Okay, so continuity. Now, continuity is basically talking about whether or not a function is continuous or not. So the first idea we're going to talk about is that a tangent can only be drawn at a point if the curve has no break at the point and there is no sharp corner there. Okay, so those are the only two situations in which we can draw a tangent. Okay, so for continuity at a point means there is no break in the curve at that point. Okay, so if we at all have a curve, then it's not, or the function's not continuous there. Okay, this is an informal definition, but it will be enough for what we need to use it for. Okay, so let's have a look at two different types of functions. Okay, and we'll draw them up really quick. So this is function number one. Let's draw a line that's actually straight. Okay, 1 and 2. Okay, and this is our function number 1. Okay, and it's just a parabola, like that. And this will be function number 2 over here. Okay, and this function is going to look like this. And it's going to come down like that. Let me draw it a bit better. Once again. Okay, and then it's going to have a bit come around like that. Okay, what do we notice about these two functions? Well, number one, if we have a look at the first one, this is a continuous function. This is an example of a continuous function because if we started at one of the points and drew it all the way along and copied it down, we'd be able to draw this whole function without lifting up our pen once, okay? Just like that. Whereas if we look at the second function, okay, it goes up here, okay, and it goes up this way forever and forever and ever, but then it reappears back down here, okay? And once it keeps going that way, then it comes back down again from here, okay? So what we notice about that function is it's not continuous, okay? And it's just by the sheer definition. So a function f of x is called continuous at a point, so x is equal to a, for example, if the graph of y of f of x can be drawn through the point where x is equal to a without lifting a pencil at a point. So let's say we're looking at 1 in both of these cases. Okay, so in the first function, okay, it's continuous at this point because I can keep drawing through that one value there. Whereas on this one, my 1 value, okay, has that obvious break coming down that way there. Okay, if there is a break in the curve, we say that there is a discontinuity at x is equal to a. So in this case, we would say discontinuity at x is equal to 1, okay, in this case. And we'd also say there's one at x is equal to -1 as well, okay? So that's essentially what the continuity and the continuity and discontinuities are. So we're going to make an assumption in our course, and it's quite obvious that a function such as y is equal to x squared is continuous for every value of x without further formality. And we can make this general assumption of continuity as loosely as the fact that the functions in the course that we're going to be doing, so in Mathematics Advanced, are continuous for every value of x in their domain except when there is an obvious problem. Now, what I mean by an obvious problem is, let's say we had the function, okay, y is equal to, or f of x is equal to 3x plus 3 over x plus 1. Okay, so if we look at this function, we could say to ourselves, well, we can simplify this a bit. This thing simplifies to 3 lots of x plus 1 over x plus 1, in which case we can say both the top and the bottom cancel out. So when we draw the function, when we draw this function, okay, when we draw this function on a graph, well, that's too big. When we draw this function on a graph, okay, like this, okay, it's just saying, well, at 3, we have a function that goes along like that. That's what this function's saying. However, there is a problem. because our original function is this one over here, okay? This is the original function. So y is equal to 3x plus 3 over x plus 1. If x is equal to -1, so if x is equal to -1, then the denominator doesn't actually exist, so the denominator is equal to 0, and therefore the function doesn't actually exist at that point. So at x is equal to -1, there's going to be a hole here in this function. So what the function will actually look like, is it will look like just the function y is equal to 3, but with just a big hole in the middle there. So the simplifying does work, and you can do the simplifying, but you just need to keep into consideration what the original function was, okay? Because we have that x plus 1 on the bottom of the function, we can't actually have a value of -1 into this function. So what we say is our function f of x is equal to 3, except x cannot be equal to 1, or provided that x is not equal to 1, okay? So that's pretty much it. Now, we're going to be mostly concerning ourselves in this little exercise about piecewise functions. Okay, and as a reminder, a piecewise function is a function that looks something like this. So let f of x be equal to 9 minus x squared for y is less than or equal to 0, or 9 plus x for x is greater than 0. So what we're going to do is we're going to find f of 0 first, and then construct a table of values to establish whether the graph is continuous at x is equal to 0. We're going to then sketch the graph and hence write down the domain and range. So we'll start off with part A, and it says find f of 0. So f of 0 is equal to, okay, well let's put both f of 0 into this one here, and it says, well, when f is equal to 0, we have to use this equation here, okay? And we'll try and substitute in the other one and see what the other value is. So f of 9 minus 0 squared, well, that's just equal to 9. And we've also got f of 0 is equal to 9 plus 0, which is also equal to 9, okay? So when we draw up our table of values, okay, we're going to have our x, and we're going to have our f of x, and we're going to go -2, -1, 0, 1, 2. So at 0, we've got 9. Now, if we're putting in positive numbers, we're going to be using our second identity, or a second definition. And if we've got negative numbers, we're going to be using the first. So substituting some values into the into the positive. So we'll do 1 and 2 first. So 9 plus 1 is 10. And 9 plus 2 is 11. And going the other way, we've got 9 minus -1 squared, so that's just 1. So 9 minus -1 squared, so 9 minus 1 is 8, and then 9 minus -2 squared, so -2 squared is 4, so 9 minus 4 is equal to 5, okay? So it's basically a parabola on the left side and a straight line on the right side, okay? So find constructed table values to establish whether the graph is continuous, not continuous, like I've got written there, at x is equal to 0. It is, because essentially both of the function values are going to be the same. So it's going to sort of hit this point where they're both the same value, and then it's going to start doing something else. So part B is to then draw this. So what I'm going to do is I'm going to draw quite a big Cartesian plane for this one. Okay. It's going to be something along like this. Okay. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3. 1, 2, 3. Okay, so at 0, it's 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, which is that part here. I might use a different color. So 9, at 1, it's 10. So at 1, it's 10. At 2, it's 11. So we've got this straight line on this side. And then on our other side, we should be including the point from this one. Okay, then we've got -1, 8, so it's going to look like this. And then we've got -2, 5, so -2 is across here, and then -7, 6, 5, and that's this one here. So this one will come back down, something like that. As you can see, it's not perfect, but it is sort of a continuous line. It sort of goes up like this and then shoots across like that, okay? And that is what our sketch will look like for this case, okay? Part C is hence write down its domain and range. Well, the domain for this case, so what x values can I have in this case? Well, it's all, so all real x, and the range, well, the y values I can get back out are all real y values, okay? So I'm always going to get something along here and something down here, and I'm always going to be able to put something into this function. Okay, so that's example number 1. Let's have a look at a second example where we've got where we're going to test whether or not a piecewise function will join up. So what we've got here is what a three-way, I guess you'd say, a three function, piecewise function. And what we're going to do is establish if the graph is continuous at 3, and you'll notice that all our points here are around 3. They're all are based around 3. Okay, I'm going to sketch the graph, and then we're going to write down the domain and range. So with this one here, we have got 2 to the power of x for x is less than 3. We've got x is equal to, we've got 8 for when x is equal to 3. And we've got x squared for when x is greater than 3. So to determine if it's continuous at 3, we're basically going to just check 3 at each of these points here. Okay, so at 3, it's equal to 8. Okay, then we're going to substitute, so sub 3 into, and it's not going to be x first. We're going to go to the x to see what it is. So 2 to the 3, which is equal to 8. So yep, it works for that one. And then we're going to substitute it into x squared. So that is sub 3 into x squared, which means that we're going to have 3 squared, which is equal to 9. So that means it's not continuous. Okay. So when we sketch this thing, okay, just a quick sketch down here. Okay, we're going to have our function going to be 2 to the power of x. It's going to go like this, and when it gets to 3, so this is our value for 3. Okay, this should be at 8. Okay, and then what's going to happen is our other function is going to take over at 9. Okay, and it's going to continue going like that. Okay, so there's going to be that little jump between the two where the function is going to swap over and it's going to keep going in a different style. And so there's this break here, and so we won't be able to actually draw a tangent at that point there. Okay, so with that being said, let's finish off by writing down what the domain and the range are. So this is part C. Okay, so the domain for this one is everything, okay, because we can put any number into this. Okay, we can even put 3 into this function, original function back up here. If we put 3 into this, okay, it's telling me that I need to have 8. Okay, and I can put anything less than 3, and I can put anything above 3. The only issue is that my range is going to be a little bit different. Okay, so my range is going to be a little bit different. Okay, so from negative infinity, oops, sorry, not negative infinity, tell a lie. Okay, and these should be open brackets, not closed brackets too. Okay, so my range, so even though I can put negative infinity into this thing, this function never actually drops below the x-axis, because the left-hand side function is an exponential function. It's 2 to the power of x. So the range is going to be from 0, and it's going to go up to and including 8. So it's open bracket on the 0, fat bracket on the 8, like that. Okay. So basically everything from here up to the 8 is part of the domain. I can't have anything here in a negative. I also can't put a number in that's going to get me something between the 9 and the 8. Okay. So on the other side, we're going to have our open bracket on the 9 and everything else up into infinity. So there's this gap here as well where we can't get the y value. And so there's going to be no point in that value there. So there's going to be no x value I can put in. So there's no part of my domain I can put into there to get something out. So the range won't cover that area there. And it also doesn't cover the negative as well. So that's our domain and that's our range for this one. Okay. So with that being said, that is going to be the end of our continuity. After this, we're going to look at differentiability, and then that will finish us off for the topic. Okay. One last thing I want to mention is that the continuity pretty much falls straight into the differentiability, okay? And we'll have a look at all of this. So basically, all the stuff that we've done in this one is going to play a massive role in the stuff that we're going to be doing in the next exercise, I guess you'd call it.